Tonight we're trying to evaluate an expression that depends on the roots of a particular polynomial. Now notice this particular polynomial, we don't even know what s is. That's what makes this sort of fascinating. S is just some real number. We don't know what it is. It turns out that s is minus the sum of the roots, which really doesn't, it's really not important as far as this problem goes. But notice we have 2 root 11, the coefficient of x, and then minus 2024 is the constant term. Any third degree polynomial has 3 roots. Some of them may have multiplicities of 2 or whatever, but it has 3 roots, and we're calling them a, b, and c. And we're supposed to evaluate this expression without calculating a, b, and c, which of course you really can't here since you don't know what the coefficient of x squared is. But it turns out there's enough algebraic structure here. Now let's move along and see how we might go about this. Okay, now this is kind of a standard approach right here. You expand the cubic out, and the factor theorem says that if you have like for example, if you have a root c, then x minus c is a factor, right? And similarly for the others. Okay, so that's what we got here. We have this expansion. When we expand it out, here's what we get. And you can see right off what's going to happen right here. You're going to have minus abc is going to be equal to minus 2024. So this is going to imply that abc is equal to 2024. Now the reason why we're taking this approach is because you can see nothing but a's, b's, and c's in here, and you think maybe there's going to be some simplifying algebra here where a term like this might be present in the simplifying algebra. We're going to try to combine this pair of fractions, this difference of 2 fractions, to a single fraction. Okay. Now also the coefficient of x is the product, the pairwise product of the zeros summed up, and so you can see right here that 2 root 11 is directly equal to ab plus ac okay, plus BC. Okay, and that's just by inspection, folks. Now you may wonder again, why are we even interested in this? Well, just take a look at the object we're trying to evaluate. See, it does have the appearance of this. This is sometimes called elementary symmetric polynomial of degree 2, I think. But notice it appears twice, and we actually know the value of it. All right, right here we have it right here in our greedy hands. You know, it's equal to 2 root 11, but the rest of it's kind of unresolved at this point. Okay, so let's move along and see what happens here. Now I did all the algebra. I know you guys would enjoy watching me write it out, but the very first step right here is just common denominator. All I did was multiply this top and bottom by this object to get a squared, which is over here, you see. So we have a multiply through by the appropriate version of 1 to combine the two fractions into a single fraction. Okay, now right here we get the AB quantity squared, which is going to cancel with this AB quantity squared. And so we're left, when you subtract all this off, this is what you end up with, folks. Again, the AB squared terms cancel nicely. All right, and then what you can do is factor it like this. Okay. And again, you guys can follow along. I don't feel like there's no need to talk through every bit of that. But you see, we got lucky right here because we have what we're looking for. We have ABC, which is known. Remember, we know that ABC is equal to 2024 here. Okay, and so also we notice that these two binomials will cancel. And of course, we're assuming that a plus b is not equal to 0 here. Okay, but notice that we're done. Okay, because this much cancels. We know that ABC is 2024. Okay, folks, and then let's see. AB plus BC plus AC is this guy squared, right? We have to square it. So that would be, if you square 2, you get 4, and you get 4 times 11 is 44. So you see that would be over, well, I'll just write it out for you guys. It would end up being 2 root 11 quantity squared. Right, folks? And sorry, it's hard to keep all this on one screen, but that's just based on what we observed up here, comparing the given to this expansion here. Okay, so what does that end up being? This is equal to 2024 divided by 44. I think that's 46. Anyway, I'm not sure. I think I'm pretty sure that's 46 if I remember. Okay. So anyway, y'all, this is definitely the answer right here. As far as I know, it's equal to 46. I don't have my calculator handy. Anyway, that's it, folks. Kind of nice. And that is kind of neat. And if you wanted to do this, you could use some kind of programming language. Any real number, it doesn't matter. If S is 0, the product, all these roots, this expression here, would evaluate to 46. If S were anything, S were any real number, and that, to me, that's amazing. And I don't know if it's just the structure of these partial sum looking things, but this expression that we're trying to evaluate through a not too difficult sequence of algebraic transformations gives us something that's unequivocally you can evaluate it without a problem. So anyway, to me, that's kind of intriguing to have an unknown coefficient of x squared, and yet the algebraic structure is such that you can actually pull out a concrete solution. Anyway, I guess that's all I have to say. Thank you for viewing.